Good afternoon, everyone. My name is David Olefelt, and I'm a professor at the University of Alberta in Edmonton. And I'm going to give you a brief overview of the Boreal-Arctic Wetland and Lake Dataset, BALD. And this is a series of projects that I've been working on jointly with Mackenzie Kuhn, who's an assistant professor at University of British Columbia in Vancouver. So Kenzie and I started working on this, it's almost 10 years ago. And our primary goal was to refine bottom-up estimates of boreal Arctic methane emissions. And the two low-hanging fruits where we saw that we could make an improvement, the first one was in most upscaling of northern methane emissions, there was an assumption that there's only one type of wetland or one type of lake. And as a field researcher, we know this is not the case. We know that there are distinct differences between different types of wetlands. And then the second low-hanging fruit was that in many cases when upscaling was done, it was either done for wetlands or for lakes. And there is a risk when you do them separately that you're not paying attention to overlaps. Where does a wetland start and a lake begin? And by doing them in a joint framework, we were hoping to avoid this type of potential double accounting. So the approach that we chose to do was to have, well, there's three publications. The first one is a land cover database, which uses what I'll explain later on, but an expert assessment to arrive at the distribution of several wetland and lake classes. And then we pair that with a literature synthesis of published flux data, especially based on chamber measurements, both from wetlands and lakes. And the thing that holds these two together is that they use the same classification scheme. And that means that we are then able to combine the land cover with the flux data set seamlessly. And that's a publication that came out last year, about a year ago, where we then provide a new estimate for current and future methane emissions. So as mentioned, right, the one thing that holds this project together is that we're using a methane-centric classification, both for wetlands and for lakes. And for wetlands, we're using a modified version of the Canadian Wetland Classification System, which classifies wetlands primarily based on their moisture regime, so average water table position, and then their nutrient regime from poor to rich. And in this, they also end up being their dynamics, their hydrodynamics. So for non-permafrost wetlands are dry, nutrient poor. These are bogs. Slightly wetter, more dynamic, nutrient rich, we have our fens, and then we get to marshes that we generally find along edges of lakes or rivers or so. And in our BALD system, we also decided that we're going to make permafrost conditions as one of our key determinants of classes. So then we also have permafrost bog, which are really dry bogs with a frozen core. And then we have only one other class for our northern wetlands, and we call this tundra wetlands. And this is perhaps, if I could go back and rethink my wetland class, I probably would have split the tundra wetland into something like a moist and a wet tundra. It ended up being giving us some grief in our upscaling towards the end. For lakes, we decided that we were going to go with both size and genesis of the lakes. So we have large, mid-size, and small lakes. And then for the mid-size and small, it really matters their genesis. We have our peatland lakes, which either have thick organic sediments at the bottom or in their surroundings, Holocene primarily material. And then we have our Yedema lakes, which are these Pleistocene, organic rich but mineral soils, often highly labile. So we know that these have distinct methane emissions when we compare it to other types of lakes. We're calling it glacial lakes here, but really it's pretty much anything that does not fit in the peatland or Yedema bins. And then Kenzie updated the database of fluxes. And this is what we went through the literature, and for each publication, we looked at the site descriptions and we used the Canadian classification system and put them in that bin. And then this is sort of the methane emissions from each one of them. So it shows that this classification system yields classes which have distinct methane emissions. High emissions from marsh, low emissions from bog, and almost none from permafrost bogs, and similar for our open water ecosystems. And here, this work, the bald methane database, has also now become part of the ABC Flux version 2. The Kemsey put together this one, bald methane. It has primarily chamber-based measurements, and then in ABC Flux, it includes also eddy covariance and other approaches of measuring methane emissions. And Kenzie's also working on a next update for this data set, where rather than only having seasonal averages of fluxes, it's now going to be coded by month as well, which would help for modeling and upscaling. So then back to the issue of then having a land cover data set that matches this land cover classification system. And there are no direct observations at the Pan-Arctic scale which differentiates between these classes. So I decided to go sort of for a shortcut by using an expert survey, an expert assessment. So the way this was done was, well, we decided we'd have half-degree cells for our resolution, and then we imported 16 data sets that we thought had indirect data of helping us understand the distribution of different classes. So this was data sets that had information on topography, climate, soils, permafrost conditions, total wetland area, total lake area, open water, and some of the seasonal inundation. And then I enlisted about 30 researchers who have field experience from working in the north and particularly associated with methane measurements. And each one of them got about 20 of these cells. They got to look at Google Earth imagery and the data from these 16 data sets. And then they were asked to give their estimate of proportional distribution of these different wetland and lake classes. So that gives us a training data set of about 700 cells. And then we used machine learning to then derive at the distribution of the different wetland and lake classes in the ball data set. So this is what we ended up with. And so distribution of each of the classes. And I would say here that the total wetland area is very similar to some of the previous products. So the total wetland and its distribution is not novel. What's novel with BALD is that we then have this reasonable partitioning between wetland classes, which is driven by the expert assessment. And similarly for lakes, we end up with this type of distribution. And here, I'm quite humble in the understanding that an expert assessment, of course, will have biases. I do think it gives us roughly a reasonable estimate of how these different wetland and lake classes are partitioned in the landscape, but they aren't direct observations of them, and that's important to keep in mind, right? And I am looking forward to seeing new products that takes the approach of methane-centric land cover classification, but maybe is able to use newly developed remote sensing and GIS approaches to refine on this. Because I do think that we are onto something very important with the BALD project here in using these methane-centric land cover classes. So here is now when we start putting together the land cover and the flux database, we can start seeing things like, for example, permafrost bogs. They have a large area, but they have very small emissions on a per area basis, which means that their total emissions are very low compared to other wetland classes. And conversely, you have something like marshes, which actually just cover a fairly small amount of the total wetland cover, but per area they have really high emissions, which means that marshes have the second highest emissions just behind fens. Our approach also here allowed us to look at the sources of uncertainty, whether they were based on field data and fluxes within each one of these classes, or whether they were based on area uncertainty, basically on the disagreement between the different experts on the distribution. And for wetlands, this reinforces the idea, or the take-home message is that area uncertainties are greater than flux uncertainties. So if we want to improve wetland modeling, then actually having better land cover maps is more valuable than having more field data at this time. For lakes, it's slightly different. Here, lakes, well, we have less data overall, and there's more variability owing to the episodic nature of ebullition and differences in methodology on how fluxes are measured and how you stratify sampling from edges to center of lakes, for example, which shows that we actually are more in need of field data rather than perhaps the spatial products. And then overall, our estimate of total methane emissions through this approach ended up being lower than previous bottom-up estimates, largely because accounting for large wetlands which have low emissions, like the permafrost bogs, and for lakes that we gave large lakes really low methane emissions as part here. So accounting for those low emitting wetland classes was important. We could also look into the future or play with scenarios. And with our data set, we have these two things that we could separate the effects of. We could look at the individual effect of permafrost thaw by using transition rates due to permafrost thaw. So where permafrost peatlands or wetlands turn into non-permafrost wetlands, and also rates of lake drainage or expansion from one type to another. And then we have climate warming, which is basically the temperature dependency within a class, and also the dependency on the length of the growing season as our climate warms up. And doing this, we find that the main effect is from climate warming. So lengthening of the season, warmer soils is a greater effect than the abrupt thaw, which causes transition of one wetland type to another. In a central warming scenario, our approach says that we have sort of a modest sensitivity of total methane emissions. They can increase by about 30% by the end of the century. And primarily this is due to increased emissions from fens and marshes, which both expand laterally because of thaw, and they warm up and have longer seasons. So some final thoughts on this project. Well, I do think that our approach shows that having a methane-centric land cover classification is absolutely crucial if we are to estimate our current and future methane emissions. And then the bald spatial data set, based on the expert survey, I think it provides sort of a proof of concept that this approach of accounting for different wetland classes is really important. But I also acknowledge that I think that there is lots of room for improvements here, especially as there's new direct and indirect remote sensing data coming online and new AI capabilities. So with that, I'll round off and thank you guys for listening.